For the duration of our civilization's existence, humanity has grappled with the seemingly straightforward yet perplexing question of how the universe came to be. It wasn't until the mid-20th century that a significant breakthrough occurred, the discovery of the cosmic microwave background. This amazing discovery quickly made a connection to the lingering, low-frequency radiation that the Big Bang Theory predicted. Since then, our comprehension has undergone continuous refinement, allowing us to estimate the universe's age at approximately 13.8 billion years and identify its current composition, an intriguing amalgamation encompassing dark energy, dark matter, the familiar constituents, neutrinos, and photons. This knowledge is enough to establish expectations about how and when the universe should have generated stars, galaxies, and even groups and clusters of galaxies, paving the way for the formation of our contemporary cosmic web. The basic details, however, of how rapidly the universe grew up to stellar, galactic, and supergalactic sizes remains outside the reach of our finest earlier observations, such as Hubble. However, JWST changes that element of the tale by answering these questions for the first time. It has uncovered the oldest proto-galaxy cluster yet detected, 650 million years after the Big Bang. And here is what this discovery tells us. In theory, the universe has a hierarchy of how things develop. The universe was almost uniform in the early phases of the hot Big Bang. All matter and energy were dispersed uniformly throughout space, with small, 1 part in 30,000 perturbations overlaid above that constant backdrop. These oscillations are caused by cosmic inflation, which preceded and established the Big Bang, and they exist on all cosmic scales: tiny, intermediate, and huge. Because matter and radiation interact as the universe expands, the smallest scale fluctuations are wiped out. The intermediate scales have peaks and troughs, and whether density fluctuations are boosted or repressed, and the enormous cosmic scales remain untouched. This information is contained in the Big Bang's residual glow, the cosmic microwave background, where it may still be seen today. The overdense regions then begin to develop gravitationally, while the underdense portions give up their matter and energy to the denser surroundings. Despite the idea that gravity is an infinite range force, gravitational growth does not proceed evenly throughout the universe. The critical thing to understand is that gravity, like other messages in the universe, does not reach everywhere instantly, but is instead restricted by the speed of light. If you have an overdense region in space, it can attract matter nearby in a certain amount of time. Still, matter that is 10 times as distant will take at least 10 times as long, probably slightly more, given that the universe is expanding, to feel the gravitational attraction from the same object. The longer it takes for gravitational pull to begin, the greater and grander the cosmic scale, from star clusters to galaxies to groups and clusters of galaxies and beyond. Galaxy clusters that are heated, such as by the collision of fast-moving gas clouds, or by intense star formation processes, release X-rays across the intergalactic medium within the cluster, leaving an identifying signal if we probe them with the appropriate wavelengths of light. These X-ray producing clusters help identify clusters and learn about their masses, gas contents, and merger histories. Various galaxy clusters have been discovered by studying the collective effects of their gravity, the phenomena of strong and weak gravitational lensing. A massive galaxy cluster will be distinguishable from a set of unclustered galaxies due to the lensing features caused by intracluster matter, the mass within the cluster that exists between the individual galaxies. CLJ 1001 plus 0220, identified by its X-ray emissions and whose light we see 2.7 billion years after the Big Bang, is a reasonably nearby mature galaxy cluster. It contains 17 distinct galaxies, more than half of which are starburst galaxies, forming stars in a massive burst that spans the whole galaxy. Galaxy clusters, on the other hand, do not begin as mature objects, but rather grow from an unformed condition through a proto-cluster phase. To identify the first such objects, we must seek proto-clusters of galaxies, groups that haven't yet heated their gas enough to generate X-rays. A 2019 survey using premier ground-based observatories such as Subaru, Keck, and Gemini revealed 2 very distant collections of several galaxies in the very early universe. one consisting of 44 galaxies at a redshift of 5.7, corresponding to an age of 1 billion years after the Big Bang, and another consisting of 12 galaxies at a redshift of 6.6, corresponding to a period of 800 million years after the Big Bang. These proto-clusters were the first examples of groups of galaxies at a relative location in space, with their speeds and masses showing that they are clearly in the process of becoming gravitationally linked and may have already exceeded that threshold. We fully anticipated shattering this cosmic record with JWST's unparalleled cosmic vision, stretching the earliest known cluster back to unimaginable periods. However, it was assumed that this would take some time, since reliably detecting galaxy clusters often necessitates the coexistence of two datasets. First, you'll need a wide-field photometric survey that can cover a big enough region to identify galaxy cluster candidates, galaxies whose colors are consistent with them all being very distant and at the same distance. Then, you must be able to run spectroscopic follow-ups on those galaxy candidates to determine which are genuine galaxies and what their actual redshift or cosmic distances are. Panoramic and Cosmos Webb are the only two proposals remaining in JWST's first year of science operations, which we're still in, and neither has reported their findings. 3 more first-year surveys, however, covered lesser areas. JD's, the JWST Advanced Deep Extragalactic Survey, GLASS, which examined the deeply lensed galaxy cluster A-Belt 2744, and SEERS, the Cosmic Evolution Early Release Science Survey, have already published their findings, with SEERS discovering 4 galaxies in the same narrow area of sky at the same distant redshift of 4.9, corresponding to a proto-cluster just 1.2 billion years after the Big Bang. However, within the GLASS field, where the impacts of a magnifying foreground galaxy cluster, A-Belt 2744, are included, the potential for delving much deeper abounds. As luck would have it, and as far as we can tell, it is truly just luck, 7 independent galaxies have been discovered in the same region and spectroscopically confirmed to be at the same redshift, 7.88, which corresponds to a time 650 million years after the Big Bang, the earliest proto-cluster of galaxies ever identified. The cluster's name, at least for the time being, is rather long, A2744Z7P90D. The Hubble Space Telescope previously examined this galaxy cluster, which revealed over 130 times the average number of galaxies inside a fairly tiny region of space, which includes this newly detected proto-cluster. The most intriguing galaxy candidate from the Hubble research, however, was designated YD4, and it now turns out to be at a redshift of 8.38, indicating that it's not a member of this proto-cluster but rather a still more distant background object. This work not only reveals the most distant known proto-cluster of galaxies in the universe to date, but it also emphasizes how crucial it is to detect and spectroscopically validate all of the distant galaxy candidates that we anticipate will belong to a single entity. The previous Hubble analysis predicted a considerably larger, more expansive proto-cluster than exists. There are only roughly 24 times the number of galaxies in this cluster, rather than the previously anticipated 130. Some of the galaxies discovered were not related to the proto-cluster, but rather were found somewhere along the line of sight. Furthermore, several potential galaxies still lack spectra, emphasizing the significance of monitoring them. The authors also attempted to quantify the mass and velocity dispersion, how quickly galaxies move relative to one another inside this proto-cluster, and discovered something astonishing. The aggregate mass of the 7 component galaxies is around 400 million suns, which is almost the mass of the present Milky Way, and therefore places a lower limit on the mass of the proto-cluster. It should have expanded to at least 5,000 times that size by now, or to the mass of the modern-day Coma cluster. And while the predicted velocity dispersion of 1,100 kilometers per second is somewhat questionable, it appears to be strikingly compatible with known high-mass galaxy clusters. And now from this discovery, we can witness how the universe grew up rather than simply assuming. We're building a more complete, comprehensive, and accurate picture of how our universe evolved from a small, star-free, nearly perfectly uniform state to our massive, galaxy-rich cosmos of today, thanks to the JWST's incredible capabilities and the remarkable work of the scientists acquiring and analyzing data from the distant universe.